A block of mass 2m is placed symmetrically on two identical wedges of mass m, as shown. All surfaces are frictionless, and the wedges have angle theta to the vertical. If the system is released from rest, what is the downward acceleration of the block? Let's place the origin of x-y coordinate system at the center, and define the displacements of the right wedge and the block as x and y. The yellow angle complements the angle theta. Since the block is rigid, half of its length stays constant as it comes down. Therefore we can express half length of the block in terms of x, y, and theta. Accelerations of the objects can be related to each other through this equation by taking second derivative of both sides and considering the definitions and the vanishing terms. Since surfaces are frictionless, contact forces on the block are perpendicular to the surface. The right wedge will be under the influence of an opposite reaction force. The vertical component on the wedge is countered by the ground. However, the horizontal component is unopposed and accelerates the wedge to the right. The block will accelerate under the influence of gravity as well as the symmetric vertical components at each side. We obtain two more equations applying Newton's second law for the block along y-axis, and the right wedge along the x-axis. One additional equation is obtained through the right triangle formed by components of the normal force. The ratio of the magnitude of the components provides the tangent of the angle theta. Overall, we now have 4 equations and 4 unknowns, nx, ny, ax, and ay. We can solve the system of equations to find each one of the unknowns. An equation for ny is obtained through the third equation, after simplification and rearranging the terms. We can also use first, second, and the last equation to arrive at an alternative equation for ny. Equating these two equations and remembering the trigonometric identity of sum of squares of sine and cosine, we find that ay is g cosine square theta.